Hi everyone, today I want to talk to you about event-driven terminal workflows. We process a lot of events on the system and kernel level, but mostly those are untapped powers or potential. And I want to show you a few ways to do this, both within using tools and workflow, as well as in bash scripting. So let's define the problem. I think if you worked with software and closely with the terminal, you probably stumbled upon one or all of those challenges. For example, you change a file, and every single time when you change it, you have to run tests or rebuild something or react in different way. There are plenty of programs currently. Every language supports one way or the other hot reload. So this is this class of problems. We are reacting to an event, which is a file change. Various kinds of system events, for example, system producing logs, various statuses. This is often something we want to watch, maybe in a dedicated terminal pane, if you are troubleshooting. And based off of certain patterns that we recognize there, we want to react to it, maybe be notified or something like this. Finally, some form of alerting, whether this is a file change or a system change or a different event, we would like to be notified. So either directly within the terminal, visually see that something changed, or maybe have more sophisticated forms of notification. Lastly, process lifecycle. Think of, this is probably a little bit more related to scripting. You want to clean up your resources when you don't need them. Maybe you need to restart a process or a service, or broadly speaking, maybe you need to react on a signal that the system sends you. So if you find yourself manually processing one or more of those types of events, then this video is definitely for you. Let's set the stage by discussing some basic concepts. So first concepts I want to briefly talk about is IPC. It stands for Internal Process Communication, and every operating system, I'm talking mostly about Linux, but this concerns equally macOS, Windows, or other systems. Every operating system has a way of enabling processes to talk to each other. So by process, we simply define a standalone encapsulated memory segment and a process that has its own identity and can be addressed by other processes. So processes cannot talk to each other just by default. They need to use some form of communication in between them. And we have a few of those communication patterns available. The most common pattern that you definitely used if you work with terminal at all is pipes. So this is data streaming pattern where we base our communication off of a text as data. So we have simple text streams, and then we take the output of one command and pipe it as an input to another command. So this is a very common way of inter-process communication, but there's quite a few more. This list is not exhaustive, but those are most popular methods. So first of all are signals. This is a low-level system way of letting us know that something happened within the process, and also giving processes an ability to signal that something just happened. So this can be both used as on the receiving end or on the producer end. So we as script creators can send a signal, and we can also react to a signal. A very common signal that you would like to react to is either a kill signal or a hold signal, and then if you write your program in a good way, you will have ability to intercept the kill signal and gracefully shut down and clean up your resources and sub-processes if you have any before shutting down. So this is a very common and kind of a foundational way of how our programs and tools can communicate between kernel and the user space through signals. We have also sockets, which is a bidirectional channel. So this is Unix domain sockets or WebSockets, and they are more kind of formal, more a little bit heavier way of communicating. We're not going to cover them in this video, but let me know if you're interested. Would be happy to talk about them. We have also dbus, which is desktop message bus for notifications. This is Linux specific, but all the systems have similar ways of notifying and using events. As I mentioned, there's more, but just wanted to set the stage that in order to be able to receive events and produce them and react to events, we need to understand the basics of how processes in our system communicate. So what are events, real quickly? So this is very intuitive, but I wanted to quickly go through it. So an event is something that happened that we can react to, as simple as that. It can be literally anything, a state change, so a file has been modified, process exited, something was opened, closed, and so on. It can be signals, as I mentioned earlier, messages, timers, anything literally that we can categorize as an action being taken within the system. Events are by design asynchronous, meaning something happens and we can intercept it or we can react to it. What it means is that most of the events that our system produces are non-blocking, meaning we just intercept an event and system just produced it. There are ways to block on events, of course, but just the basic events that are getting from our system are asynchronous. So we don't know when the events will happen. I mean, we have some ways of predicting them. If we close or open a file, then we know that the event will happen, will be triggered on close or open, but we don't maybe know when the file will be processed. So this is an interesting property of an event. And we define what we need to do when the events occur. So combining those two things together, we have event sources, for instance, a file change, and we have an inter-process communication method. This is not one-to-one, I just use them as an examples. So file change, and you can use notification mechanism, and then you can either let the system notify you, as we will see in a second, or you can use your tool. Then maybe you intercept a signal, and using a kill command, you can send the signal. By the way, kill command is a little bit of a misnomer. This command doesn't only kill processes, it can send any event or any signal to a process, including kill, of course. Maybe a timer fired, something happened on cron, and you want to intercept it with dbus. So this is how we can combine events and internal process communication. So in terminal, I created 4 categories where it's very common, at least for me, to interact with various events in these 4 categories. So one is command polling. What it means is simply, and you've done it definitely several times already, whenever you have to watch continuously for command outputs. Maybe the output of a command changes over time. Things like observing logs, or in case of Kubernetes, which I work with often, I want to observe pod statuses or events, maybe network stats, anything that can change over time. I have a dedicated pane in my terminal where I can capture all those things. Another category is file and directory watching. So essentially anything that can change on the disk, whether those are timestamps of files, maybe something was modified, saved, deleted, a directory was created, any operations that are performed on disk, you can also watch for it. And a very common example is running test suite or refreshing a web page if you're working with a web application on file save. Notifications, so anything that can send alerts, and I do it very, very often, you can see also on top here on my screen, this few custom kind of alerting structures here that I use a program called Argos on Linux. So it's a way to notify myself when something important happens. And then notification is essentially kind of like one of the ways I can know that event happened, or maybe it notifies me and expects me to do something. So there's various use cases in this category. It can be, for example, notifying you that the long-running process finished. Maybe it was a very long build or testing suite or something. And notifications in terms of terminal, we will see in a moment what tools are available. But of course, notifications can be significantly more complex. You could send a Slack message, an email, anything you want really. And finally, final category is processing signals. This is a little bit more advanced. I'll focus on this later a little bit more. But the idea behind it is actually simple. As a script creator, if you work with bash scripts or any other programs for that matter, this is a surface for you where you can hook up nicely and gracefully into the system interface. So system will expect programs to react on certain events. So events or signals are defined within the system spec. Like Linux, for example, it has several signals that it can work with. And being, a good script developer or program developer, we would like to be able to hook to those signals. So let's start with first category. So in the first category, I have two programs. There's plenty more programs, but I just identified two, and I want to talk briefly about them. So the first category is command polling. What it does, it simply runs command on a timer. Those programs have a lot more options, but at the end of the day, this boils down to being able to say, I have a command that I would like to keep running, and I want to keep watching the output when it changes. So the two tools, one is Watch. This is a built-in Linux tool from Core Utils. You probably already have it on your system, regardless what system you're using. And viddy is a modern alternative to Watch that I like using. So here on the first line, I try to provide a bash equivalent to show you that you can use a tool like viddy, but if you don't have access to a tool, if you're writing a script and you would like to watch output of a command that you run within a script, you can do something like this. So this will enter a forever loop, clear the screen, and then in this case, run an uptime command with a date every 2 seconds. So very easy to do it without tools like viddy or Watch. Of course, it's a little bit more involving if you don't have access to them. So I definitely suggest use those tools rather than scripting. But if you don't, if your system doesn't have those tools and you cannot install them, then that's the alternative. So let's look how it works. We are going to use an ss command, which is a network observability command, and we're going to run viddy to do it. So here is viddy, and you can see that ss command outputs different values, and if there would be changes with those values, so total number of connections would change, or maybe TCP number connections would change, we would see differences highlighted within this command. Nothing changes here. Oh, we just had a one from 1365 now to 59. So the total number of TCP connections to my computer is changing, and we can see this kind of differ here highlighting briefly. So you can imagine having this open. If you're interested in output of a command, it runs in the background, and every second it changes and gives me this visual feedback that so-and-so changed, and I have this kind of insight. So that's one way of using it. So this was command polling category. Again, you execute a command, in our case ss-s head 4, and we use viddy or watch to watch for the output of the command. And in our case, we also used viddy's nice feature of highlighting the differences. Another category is file watching. So this is not only file watching, it can be directory watching, anything that changes in the disk. So we have a few tools in this category. One of them is called entr. It's available on all major platforms. Watchexec is a little newer, and iNotify wait, which is a low-level scriptable tool for Linux only. There's, again, plenty more alternatives, but they follow the same concept. They essentially check for hash changes or MD5 sum changes of a file or a directory. In terms of Linux, they might work with inodes or other elements. But at the end of the day, whenever something changes, we can then react by doing anything. So this is this typical event-driven flow. Our file changed at one end. This is our event. We realize, oh, something happened. The file content changed. And on the right-hand side, we can imagine triggering any set of actions. So common scenarios would be running test suite on file change or refreshing browser when we edit HTML or JavaScript or CSS. But in our example, we're going to do something a little bit more fun. So let me guide you real quick through the pure bash alternative. This is, again, if you don't have access to those type of tools, it's possible to do it yourself. You can then just have an MD-sum of a file, and then you check whether the MD-sum of a file that you're watching changed over a certain period of time, in this case 1 second. And if it did, you can do something, some kind of action. This is not ideal, of course. It's a little bit naive, this implementation, but it's possible to work with bash itself and come up with a relatively simple way of doing it. So let's check entr here. So we are going to list all the markdown files, and then whenever those markdown files change, we are going to output a fortune command and pipe it through cowsay, because this is cool. So let's start it. So there's markdown files that constantly changed, and whenever a file is detected, file change is detected, we have a new tux giving us some wisdom here. You are fair-minded, just, and loving. That's a perfect wisdom from tux. I'm not going to change the files here, but if I would touch any markdown file, we would see this reloading and giving us a new little wisdom. So this was a file or directory or disk watching category that you can hook into within your scripts. Moving on, we have notifications category. This is when you want to know that something happened. By the way, all those categories are very often clumped together. So you might want to watch a command in the same time. You might want to be able to react to a file and also be notified. So very often those things can be piped together or chained within a script. So a few popular tools. Notify send is a Linux specific tool, part of the libnotify library. Again, you probably have it installed. I'm not sure if it works on Mac. I don't think so. Dunstify is newer alternative, and Dunstify adds a few more interesting options here. I will show you this in a moment. And OSA script, from what I remember, is part of Mac. I don't use Mac, so don't quote me on that, but I'm sure any operating system has the same ability to notify you. So with bash, it's super simple. We can just send a terminal bell command here, and bash has a built-in terminal bell. You will just hear a terminal bell when something works. So it's very minimalistic, but it has a way of doing it. You can, of course, use some other more creative ways to do this, but it's possible to have a notification in a different way with Bash. So let's use Dunstify to show how notifications could look like. So we're executing notification, and you can see this build failed. When I click open, then it opens, in my case, GNOME editor, and just showing me this error. So it's nice, and a little bit better than notify send, because I can actually execute something from within the notification tooltip. You notice that notification appeared on top and integrated with my Linux notification system. I'm using GNOME in Pop! OS. So in your case, if you're using a different system, this could look differently. It's also possible to style this notification window or pop-up rather, and do anything. So I like using Dunstify for this reason, that I can also interact with the pop-up and maybe open a log file or do something depending on what happens. But I think this category is quite intuitive to understand, so notifications. Now let's move to something a little bit more difficult, and I want to spend some more time talking about it. So this is processing signals. Every operating system, I mean, I'm definitely speaking for Linux. I'm not sure how it works on Windows, but Linux-based systems intercept and react on a certain predefined set of signals. So what are signals? Signals, you can think of, if you come from programming background, I think it's useful to think of signals and the associated category here as events and handlers. So signal is kind of like an event that system expects and can also issue. And some of the very common ones that you definitely interacted with every day is Ctrl+C. Ctrl+C in most of the terminals produces an interrupt signal. So when you press Ctrl+C and your long-running program stops, this means that this program, the process of this program, received the interrupt signal from the system and reacted to it. Most of the programs that you interact with have ability, so person who wrote it or AI who wrote it had an ability to intercept this and react gracefully to the interrupt signal. Some other signals are term or hoop or quit or kill. So there's various signals that system expects the program to respect and can issue to a specific process. So system surface would say, okay, user clicked Ctrl+C, I am issuing an interrupt signal, I want program to stop. And then it's up for program to implement it gracefully. If not, system will force it to stop or force it to kill. But system gives you like benefit of the doubt and says, okay, I'm sending a kill signal, and if your program is smart enough to intercept it and clean everything up gracefully before system completely shuts the process down, then that's a good practice. So in our example here, we are using something that I know people are not very aware of, and I feel it's a little bit of a missed opportunity. So if you are creating your own scripts or programs, and you want to take something from this video, probably that will be an interesting part. There are two user signals that you can send, USR1 and USR2. Those are open signals that you as a programmer define. So in our case, let's go real quick to what's going to happen. First of all, we are creating here a session with bash C, and we are executing this code snippet, and ampersand signal says we are running this asynchronously, so we're just letting it run, right? First, we defined a function, which is called myCallback, and this function simply prints out this echo statement to the terminal. Then we are using a trap command, and trap command is like if registering an event handler in other programming languages. So you use trap, and you say, I want to trap the user1 signal And when the user1 signal is received, then I am going to execute the callback function. So you can see here a very, very common pattern that is in all the other programming languages, or all the major programming languages, which is being able to react on events. And typically this is done by events and event handlers. So really, really similar way of doing it. Then we're just waiting for 3 seconds and executing this snippet. And this snippet is going to run as a dedicated process. Remember, every subshell in a terminal gets its own process ID. And at the very beginning, we talked about inter-process communication. So here again, we sleep a little bit more, and we are using a built-in command called pkill. Remember earlier I said that kill doesn't only kill processes, it is capable of sending any kinds of signals. In this case, we are sending user1, and we are sending it to any process that registered my callback as a event handler. I hope you're following here. It's again very similar to event-driven programming. It's just bash related. And what is special about what I'm showing you is this user1 and user2, which is essentially an open signals that we as users can do. And this is a really nice and elegant way of reacting to custom signals. If you want to have your own custom debugging logic, let's say you send this user1 signal and then your program suddenly starts like following, rich debugging output, right? So very, very, very nice way, and I feel it's underutilized within scripts. So let's see how it works in practice. When I execute this code, you see we are waiting for 3 seconds here, and now we have signal received. So again, remember this snippet run, and then we send the pkill user signal to a process that registered my callback as a signal handler. And this is the only process that did it. Signals, by the way, are process oriented. So by default, you need to address the process either by its name, or if you're using kill, by its PID. Okay, so I hope it wasn't not too confusing and you get already some ideas how you can use user1 and user2 custom signals. If not, just the fact that signals exist and you should trap them in your scripts and you should be able to react to them would already be a really good takeaway. One thing I want to mention, kind of to situate this whole chunk of knowledge, we've learned about various events happening throughout our system. This can be file system events or directories, can be various system level events. We can produce something and this might become an event. And for ad hoc scripting, this is where we can use the tools that I showed you, and we can either do this within the terminal or wrap them in a script. But if you think of intercepting events and reacting on them on a more kind of repeatable way, more stable way, then this is typically done with systemd services in terms of Linux. There are, of course, other service runners there. But the idea is here that a long-running systemd service can essentially intercept all the signals or produce events or whatever. So it's not that you are only able to work with events in your scripting, but you can also work with events with systemd services. And this is, by the way, the most established way of how services are restarted, how they're getting updates, and so on. So signals and events being intercepted in the systemd services or other service runners. I just wanted to mention it, that just to help you situate the new, if it's new for you, this new body of knowledge with other existing systems. So a quick table, when to use what, and again, the tools that I gave you are just examples. You can search for alternatives to every tool that I talked about. Those are just the ones that I like, but there's plenty more, and they are being created all the time. So monitoring command output, my favorite tool is viddy, and it just shows you a simple diff of the command that you're running. Reacting to file save events or other system folder events, I like using entr, but also watchexec. They have slight differences, and one sometimes is better than the other, but for simple use cases, I would recommend entr. For desktop alerts, I think only for Linux. I'm not sure if Densify work in other places. It probably should work on Mac. I like using Densify simply because there's additional ability to execute an action. Cleanup on exit. If you're writing scripts, definitely use the trap keyword and learn about it. Reloading config, for example, could be done with trapping a hub signal, and then you can reload a config for your users in real time. This file watcher here, I think it's FSWatch is cross-platform file watcher, so it belongs to the first category. And then if you're building more like a production kind of service where you want to react on events on somebody else's machine, and you want to install it, then systemd is a way to go. I had a video about using systemd for pulling GitHub data. You will find it in my videos if you're interested. So a few resources, entr, viddy, watchexec. Every resource has its own page. I also left here a link to Pure Bash Bible. I tried to give you an example of how to implement each event processing as a Bash script. It's a really fantastic resource if you're writing Bash scripts, especially for systems that do not have ability to install modern tools. Almost anything that we've talked about can be done in Bash. So that's all for this video. I hope you enjoy it. As always, let me know how you are using event-driven programming tools and workflow terminals. I'm always curious how other people do it. I use it very, very often, and this became kind of my stable workflow for scripting. So when I script, I almost always have to react to a certain event or process a signal. Very, very often I use notification, and I have my own strategies of how much I want to be notified and how much of it is notification versus an action and so on. So this definitely was a journey for me. I've learned this years ago and kept on adding more and more interesting ways to interact with system events or my own events. And I feel that this is one of the strongest tools in my developer toolbox for working with scripts. All right. Thank you again. And as always, see you in the next video.